Welcome to Module 6 of the AI and Machine Learning course. Module 6 focuses on natural language processing, NLP, a branch of AI that enables computers to understand, interpret, and generate human language. This module covers key NLP techniques such as text processing, classification, sentiment analysis, and named entity recognition. It also introduces advanced NLP models and methods, including transformers and BERT. Learning objectives. By the end of this module, you will be able to 1. Understand the basics of text processing techniques in NLP. 2. Apply methods for text classification and sentiment analysis. 3. Implement named entity recognition, NER, for extracting information from text. 4. Explore advanced NLP techniques, including transformers and BERT. Natural language processing, NLP. Natural language processing, NLP, is a branch of AI that develops algorithms for computers to understand, interpret, and generate human language for meaningful interaction. NLP combines linguistics, computer science, and data science to help machines understand and use human language. It powers tasks like translation, sentiment analysis, and summarization, becoming crucial with the rise of text data from platforms like social media and news. Let's continue by exploring fundamental NLP techniques and their applications, and then delve into advanced models and methods for processing natural language. Basics of text processing, tokenization, lemmatization. Basics of text processing involve cleaning, organizing, and preparing text data for analysis. It includes steps like removing punctuation, converting text to lowercase, tokenization, and removing stop words to make the data usable for NLP tasks. Let's look at the concept of text processing. Key concepts of text processing. 1. Tokenization. Tokenization is the process of dividing a text into smaller units, such as words, phrases, or sentences. Word tokenization splits text into individual words. For example, the sentence "the cat sat on the mat" is tokenized into "the cat sat on the mat." Sentence tokenization divides text into sentences. For example, "I like apples. They are delicious" is tokenized into "I like apples, they are delicious." 2. Lemmatization. Lemmatization is the process of reducing words to their base or root form, known as a lemma. Unlike stemming, which simply trims affixes, lemmatization involves understanding the context and meaning of words to determine their base form. Example: the word running is lemmatized to run. Similarly, better is lemmatized to good. Process. Lemmatization typically involves looking up a word in a dictionary or using morphological analysis to find its root form. Text classification and sentiment analysis. Text classification is the process of assigning predefined categories to text, such as tagging emails as spam or not spam. While sentiment analysis is a type of text classification that identifies the emotional tone behind text, positive, negative, or neutral. Text classification. In text classification, we have key components that make the process effective. Techniques. Text classification uses algorithms like naive Bayes, support vector machines, SVM, and deep learning models such as CNNs and RNNs to categorize text. Process. It starts with pre-processing the text, e.g., tokenization, lemmatization, then extracting features using methods like bag of words or TF-IDF, followed by training a classifier to predict labels or categories. Sentiment analysis. In sentiment analysis, we have key components that make the process effective. Types. Sentiment analysis can be binary, positive/negative, multi-class, positive/negative/neutral, or fine-grained, e.g., happy, sad, angry, depending on the level of emotional detail needed. Techniques. It uses rule-based methods, e.g., sentiment lexicons, machine learning models like logistic regression and SVM, and deep learning approaches such as LSTMs and transformers to detect sentiment in text. Named entity recognition, NER. NER identifies and classifies key entities like people, places, and dates in text to help extract important information. Components of named entity recognition. 1. Types of entities. People. Names of individuals, e.g., Barack Obama. Organizations. Names of companies or institutions, e.g., Microsoft. Locations. Names of places, e.g., New York. Dates and times. Expressions of time, e.g., January 1, 2024. Named entity recognition, NER. NER identifies and classifies key entities like people, places, and dates in text to help extract important information. Components of named entity recognition. 1. Types of entities. People. Names of individuals, e.g., Barack Obama. Organizations. Names of companies or institutions, e.g., Microsoft. Locations. Names of places, e.g., New York. Dates and times. Expressions of time, e.g., January 1, 2024. Language models, bag of words, TF-IDF, word embeddings. Language models are tools in NLP that predict the next word in a sentence or evaluate how likely a sequence of words is. They help machines understand and generate human language. For example, when you type "I'm feeling really" on your phone, and it suggests happy or tired, that's a language model at work. It has learned from tons of text how people usually complete that sentence. In NLP, this helps chatbots respond naturally, tools summarize articles, and voice assistants understand what you're saying. Let's explore some of the language models. 1. Bag of words, BAW. The bag of words model represents text by counting word occurrences, ignoring grammar and word order, and forming a matrix of documents and their word frequencies. Features. Shows how often each word appears in a document. Limitations. Ignores word order and context, losing meaning. 2. TF-IDF, term frequency inverse document frequency. TF-IDF improves BAW by giving more weight to important words and reducing the influence of common ones across documents. Term frequency, TF. Measures how often a word appears in a document. Inverse document frequency, IDF. Indicates how unique or important a word is across all documents. TF-IDF score. Combines TF and IDF to highlight words that are important in a document but not common across all documents. 3. Word embeddings. Word embeddings are vector-based word representations that capture meaning and context, offering deeper insight than BAW or TF-IDF. Techniques like Word2Vec, Glove, and fast text create word embeddings that capture meaning and context, boosting NLP performance. Advanced techniques, transformers, BERT. Advanced techniques in NLP go beyond basic methods like keyword matching or counting word frequency. They use more complex algorithms and deep learning to help machines better understand the meaning, tone, and context of human language. These techniques allow computers to not just read text, but to understand, summarize, translate, and even respond in a human-like way. For example, chatbots that understand your intent. Basic NLP might simply detect the word help in your message like "I need help" and respond with a generic reply. Advanced NLP, on the other hand, grasps the full context. So if you say, "I can't reset my password," it understands that your issue is about password reset and offers a specific solution. Let's look at the two types of advanced techniques. 1. Transformers. The transformer model is a deep learning architecture designed for handling sequential data and capturing long-range dependencies. It relies on self-attention mechanisms to process input sequences in parallel, making it more efficient than traditional RNNs. Self-attention in transformer calculates attention scores for each word in the input sequence relative to all other words, allowing the model to focus on relevant parts of the input. Architecture. This consists of an encoder and decoder. The encoder processes the input sequence, while the decoder generates the output sequence. Advantages of transformers. 1. Transformers process data in parallel and manage long-range dependencies better than RNNs. 2. Scalability. Easily scaled to large datasets and deep architectures. 3. Faster training. Parallel processing speeds up training compared to sequential models like RNNs. 4. Versatility. Perform well across various NLP tasks like translation, summarization, and question answering. 2. BERT, bidirectional encoder representations from transformers. BERT is a pre-trained transformer model designed for understanding the context of words in a sentence. It uses bidirectional self-attention to capture context from both directions, improving performance on various NLP tasks. BERT and its variants improve accuracy and context understanding in NLP tasks. BERT includes pre-training and fine-tuning. Let's explore them. Pre-training. BERT is trained on large text datasets using masked language modeling, MLM, and next sentence prediction, NSP. Under this we have 1. MLM. Random words are hidden, and the model learns to predict them using surrounding context. 2. NSP. Trains the model to determine if one sentence follows another logically. Fine-tuning. BERT is adapted for specific tasks like text classification, NER, and question answering. Summary. In this module, you learned the basics of natural language processing, NLP. We covered text processing techniques like tokenization and lemmatization. You explored tasks such as text classification, sentiment analysis, and named entity recognition. We also introduced advanced models like transformers and BERT for deeper language understanding. Congratulations on completing the module. You've gained a solid foundation in natural language processing, learning key text processing methods and important NLP tasks like classification and sentiment analysis. You've also been introduced to advanced models like transformers and BERT, equipping you to tackle more complex language challenges. Keep up the great work.